Okay, great. Hi, everyone. Thank you for joining us. Welcome to the 71st online Spintronics seminar. It's a great pleasure to introduce today's speaker. Professor Cheng has completed his PhD in 2009 from Tsinghua University and Humboldt postdoc studies from University of Regensburg, Germany. He joined Tsinghua University as assistant professor in 2011 and now is a tenured associate professor in Tsinghua University and will probably become a full professor very soon. He works mainly on magnetic films and spintronic devices. He has published more than 180 papers in reputable journals. His citation is more than 8,000 times according to Google Scholar with H index of 46. His present research interest is antiferromagnetic spintronics and multi-field control of magnetism. He received the second-class prize of the State Natural Science Award in 2012, second-class prize of the State Scientific and Technological Progress Award in 2018, and Elsevier Chinese Most Cited Researchers in 2020. He's a young Yangtze River scholar, member of Chinese Vacuum Society, deputy director of Chinese Materials Research Society Youth Branch, and China Editorial Advisory Board of IOP Publishing. So without further ado, Cheng, please go ahead with your talk.
Okay. Could you hear me? Okay. Good morning, good afternoon, good night, everybody. Thanks for Professor Xinfan's introduction. I'm happy to do this talk by the invitation of Xinfan, Professor Xinfan, and Professor Kirill Belashenko. Maybe I'm not sure I pronounce good or not. So today I will talk about our recent work on out-of-plane spin polarization and antiferromagnetic spin Hall effect. My name is Cheng from Tsinghua University, located in Beijing. And first, I would like to talk about the spin Hall effect. Spin Hall effect is firstly by the optical observation in N-type gallium arsenide in 2004. Later, when I was in Regensburg, we tried to do this electrical detection of spin Hall effect in N-type gallium arsenide. That means we drive the current in the channel, the spin up and the spin down was accumulated at the edge of the channel. When I joined Tsinghua several years ago, we tried to do this, use this spin current from the heavy metal tantalum. The spin current flows upward and downward to switch the perpendicular magnetic anisotropy cobalt iron boron. The two ferromagnetic layers are antiferromagnetic coupled. They can be switched by the current and two different antiparallel states, herd to herd or back to back. So we demonstrated the spin orbital torque in these antiferromagnetic coupled layers. In fact, for this spin orbital torque is a long-term investigated topic, especially from 2016. A lot of people begin to pay attention to use the iridium magnets or platinum magnets, this kind of antiferromagnetic layers to pin the ferromagnetic layer to get this effective field to do field-free switching, because in general, the spin orbital torque need an assistant field. For example, here in this iridium magnets cobalt iron boron system, because of the exchange bias field, they got this field-free switching. Also, in this Tehuku group, also demonstrated the field-free switching in platinum, manganese, cobalt, nickel system. Here, the antiferromagnet also behaves as the heavy metal like this platinum and tantalum. Besides the heavy metal, this antiferromagnetic layer also serve as the exchange bias layer to get field-free switching. Before talking about our measurements, I would like to introduce a little bit about this spin torque ferromagnetic resonance. We could say spin torque FMR for short. The system is like this. This is the heavy metal. This is the ferromagnetic layer. For example, permalloy here. We got this spin torque FMR signals here. This is the raw data. The data can be divided into two parts. The first part is the symmetric part. The other part is asymmetric part, and they correspond to in-plane torque and out-plane torque respectively. These two torques can be described by this equation. For example, the spin polarization along x direction, along y direction, and along z direction. All of them has both field-like torque and anti-damping torque. In this equation, we could see x direction spin polarization, y direction, y spin polarization, and z spin polarization could contribute to the spin torque. In general, in this classic system, for example, in heavy metal platinum, in general, only the y spin polarization we call sigma y could flow into the adjacent ferromagnetic layer. So in general, we only pay attention to this sigma y phase. So we could see the angle-dependent spin torque FMR signal is quite symmetric in this case, which can be described by this equation. But differently, in 2016, Daniel Ruff's group in Cornell, they observed different angle-dependent spin torque FMR signals in tungsten telluride permalloy bilayers. They could see when the current is applied is perpendicular to the crystal mirror plane, they could see the signal is not so symmetric. This is from the contribution of sigma z. This is the first observation of sigma z in the tungsten telluride and permalloy bilayers. Later, two Singapore groups also observed the spin autoplane spin polarization sigma z in this non-collinear antiferromagnets. For example, they also use this direct observation method to observe this autoplane spin polarization sigma z. We compare two different types of sigma z in two different systems. The first is tungsten telluride. This is related to the crystal mirror symmetry. That means when the current is perpendicular to the crystal mirror, so and in this case, they could get this asymmetric signal. That means sigma z in this case. But when the current is parallel to the crystal mirror symmetry, the signal is quite symmetric. That means only sigma y in this case. In contrast, when in this non-collinear antiferromagnetic system, for example, in our group, we investigated this manganese platinum, there is a magnetic mirror symmetry. Different from this tungsten telluride, when the current is perpendicular to the magnetic mirror symmetry, there is no signal from sigma z. The signal is quite symmetric. But when the current is parallel to the magnetic mirror symmetry, we could see the spin torque FMR signals is quite unusual. After the simulation, we could get there is a sigma z contribution in this case. Then we would ask what's the difference between this crystal mirror symmetry and the magnetic mirror symmetry. Of course, they have some connections. Like this, here This is a crystal mirror. This is a polar vector. For example, current, this kind of vector is a polar vector, but for the magnetization is axial vector. For the magnetic mirror, it's different from this crystal mirror because of the time reversal symmetry is here. So because of the time reversal symmetry, the current applied direction for the sigma z is different from this crystal mirror symmetry case. Also, we investigate the generation of sigma z in this antiperovskite system. For example, manganese tin nitride. Manganese tin is quite popular in the last few years because of the large anomalous Hall effect. This is the very typical non-collinear antiferromagnet. But for this manganese tin nitride system, it also has a Kagome plane, but different from manganese tin, this is an antiperovskite system. When we apply the current parallel to the magnetic mirror, we also see this symmetric angle-dependent signal, spin torque FMR signal, indicating the existence of sigma z in this case. But when the current is perpendicular to the magnetic mirror, there is no signal from sigma z based on our fitting. So we could also say there is the spin current from sigma z in this antiperovskite system. Based on this spin torque FMR signal, we also investigate this DC measurements for very normal spin orbit torque. When we drive the current, when the current is non-X, so in this case, we could see field-free switching with sigma z. But when the current is perpendicular in is along Y direction, there is no field-free switching anymore because in this case there is no sigma z in this case. This is like this case. So we demonstrate this spin orbital torque is quite related to the auto-plane spin polarization for field-free switching. We also demonstrate this spin orbital torque switching by Mock microscope. We could see the field-free switching is indeed occurs in this system. We could see the domain switch upward, downward, and upward again by the current from positive to negative and then positive. So in this system, we demonstrate the existence of sigma z in this antiferromagnet, especially this non-collinear antiferromagnet. For this, before my introduce for the antiferromagnetic spin Hall effect, I would like to introduce the work by Otani's group in Tokyo, University of Tokyo. They observe this magnetic spin Hall effect in manganese tin. Previously, spin Hall effect was observed in a lot of systems. Just now, I also mentioned in N-type gallium arsenide, also in heavy metal, for example. When we drive the current in the channel, there will be spin up and spin down accumulation and the edge of the channel. But spin Hall effect is almost fixed after the material is prepared. This is somehow the intrinsic property of a material depending on the spin Hall angle. But in this manganese tin system, the spin Hall effect is also dependent on the magnetization. In this Kagome plane of manganese tin, they preset the magnetization along this direction and also along different direction by the magnetic field. Then they sweep a magnetic field lower than this preset field. They could see this opposite switching for this permalloy for the spin detector, indicating the magnetic spin Hall effect. They also observe inverse magnetic spin Hall effect in this system by the measurements of spin pumping. Before this spin pumping, they also set the system by these two different magnetic fields. They could see the signal is opposite, indicating the existence of inverse magnetic spin Hall effect. And then this kind of non-collinear system, they always has some uncompensated spins. That means the system is a spin unconservation. Then we try to observe some spin Hall effect in some collinear antiferromagnet. For example, magnetized gold. This is a collinear system with spin conservation. So we try to investigate magnetic spin Hall effect in collinear antiferromagnet. We select magnetized gold for our study because magnetized gold is an antiferromagnet with a high Néel temperature, and also this system has a broken sublattice inversion symmetry. Because of this special feature, sublattice inversion symmetry broken. Previously, several groups, including my group, observed the Néel Supermobile Torque in this system. And also, in this system, we demonstrated this ferroelastic strain switching of magnetic anisotropy. That means by this PMPT substrate, we switch the magnetic anisotropy of magnetized gold along two different directions. Then we observe planar Hall effect changes during this magnetic anisotropy change. So we use this system to demonstrate the antiferromagnetic spin Hall effect. So I will close the window because it's heavy raining. Okay, sorry. Then we continue. Now I want to introduce the physics picture for our investigation, the generation of sigma Z in our collinear system, magnetized gold. This is the spin structure of magnetized gold. We call this red one magnetized A. This blue one is magnetized B. When we drive the current along the Néel order along the magnetized A, so there is a spin accumulation, spin polarized carriers along this X direction. Also, because of traditional spin Hall effect, there will be spin accumulation, spin polarization along Y direction. This spin polarization along Y direction will produce spin orbit field. We can see this purple arrow. Because of this spin orbit field, the spin polarized carriers could precession to outer plane. This is sigma Z. Also, because of sublattice broken symmetry, we could see for this magnetized B, everything is opposite because of the spin polarized carriers also opposite. So, spin orbit field is also opposite. So two opposites produce the same sigma Z in this case. So a combination of magnetized A and magnetized B produce the sigma Z together. We could get a large sigma Z in this case. But differently, when the current is perpendicular to the Néel order, because in this case, the spin polarization from traditional spin Hall effect is also along Y direction. This Néel order related spin polarized carriers is somehow parallel to the spin orbit field. So there is no spin precession in this case. That means when the current is perpendicular to the Néel order, there is no sigma Z in this case. Then we try to get these two different configurations. we try to get sigma z in this case, and we move sigma z in this case. We try to demonstrate this concept later. That means sigma z is the result of n Néel order cross spin orbit field. This is sigma z. Of course, because manganese gold is somehow a heavy metal, also traditional sigma y also here. So both sigma z and sigma y can flow along z direction to adjacent ferromagnetic layer. For example, we put a permalloy adjacent to this manganese gold. This both sigma z and sigma y could flow along this z direction. This is permitted in magnetic systems. Of course, this is surprising for traditional viewpoint because only sigma y is permitted to flow along sigma z from traditional spin Hall effect viewpoint. But recently, there are some theoretical works, especially from Xiangrong Wang's group in Hong Kong. They theoretically investigate the system. For example, here, this is the spin Hall effect in magnets. From our understanding, this charge current is a vector and spin current is a tensor. In general, spin Hall angle is a value, is a constant, but a constant cannot multiply tensor, cannot get this vector. So spin Hall angle should be also a tensor. It's much more complicated than a very simple value. So spin Hall angle can be described by this equation, especially in this magnetic system. So we could get both sigma y and sigma z flowing along z direction. We grow manganese gold on the top of PMPT substrate, PMPT 011 direction. This is a ferroelectric substrate because we want to use this ferroelectric property to switch Néel order and then try to modulate the spin Hall effect in this case. This is what we want to do. This material is grown by magnetron sputtering. We got this preferred orientation manganese gold films. Because of the manganese gold, the magnetic anisotropy is quite small. It's around only 10 micro EV. So the Néel order or antiferromagnetic moments of manganese gold can be switched comparatively easily by this compressive strain. Previously, a couple of years ago, we demonstrate the easy axis of manganese gold for the original state is a non-100 direction of PMPT. But after we apply positive 4 kilovoltage per centimeter, that means after this electric field, we measure the XMLD signal. We could see XMLD signal is a reversal. Then the Néel order is a non-1 direction. It is switched 90 degree in plane. Then we apply a -2 kilovoltage per centimeter. The Néel vector is switched back to 100 direction again. This switching between these two directions, in plane directions, can be reproducible and reversible with the applying of positive 4 kilovoltage per centimeter and -2 kilovoltage per centimeter. Of course, these measurements are non-volatile. That means we remove the electric field and then we measure XMLD. We also summarize the XMLD signals as a function of the electric field. We could see the signals as a function of the electric field. This undergoes this butterfly loop, somehow a butterfly loop, indicating the ferroelastic strain is the main reason for the switching. The switching of the magnetic anisotropy of this system is important for our magnetic spin Hall effect. Then we try to demonstrate the existence of sigma z in our system. The sample is manganese gold 12 nanometers and then permalloy 16 nanometers. We measure spin torque FMR, and first we measure this field-dependent spin torque FMR signals. This is the original data. This open square signals. It can be divided into this symmetric signal and asymmetric signal. We could see here for this symmetric signal, they have the same sign, but the asymmetric signal for this negative field and the positive field, the magnitude is different, indicating the existence of strong sigma z in this case, because our current is applied along near vector along 100 direction. Just now we demonstrate in the original state, the near vector is along 100 direction. So when the current is along 100 direction, we observe this very strong sigma z, because according to this table, we could see that for this symmetric signal, the field-like torque from sigma z exists, because field-like torque does not depend on the sign of magnetic field, but anti-damping torque is dependent on the magnetic field. So based on this feature, we could demonstrate this somehow similar symmetric signal and different asymmetric signal demonstrate the existence of strong sigma z. But differently, when the current is applied along O1 minus 1 direction, this is the hard axis of new order. So in this case, because of the current is perpendicular to the new order, so here the symmetric signal has a different sign and a very comparable asymmetric signal, indicating quite weak sigma z in this case, because the new vector is perpendicular to the current. So based on these measurements, we demonstrate the sigma z is strong when the current is along the new vector. We also confirm this case by the angle-dependent measurements. This is the angle-dependent spin torque FMR signals. That means we rotate the magnetic field in plane for 360 degrees. This is the symmetric signal corresponding to the in-plane torque, and this is a symmetric signal corresponding to out-of-plane torque. We can see here that when the current is along O1 minus 1 direction, that means the current is perpendicular to the new order. The signal is almost symmetric. Only the signal from sigma y, that means the sigma z signal is quite weak in this case, because the new order is along 100 direction. They are perpendicular. Differently, when the current is along 100 direction, the signal is quite different. We can see this unusual spin torque FMR signal both for the symmetric signal and asymmetric signal. That means both field-like torque and anti-damping torque from sigma z in this case. We try to fit the signals by this equation. For this only sigma y signal, we could fit the curves by this equation: sine 2 theta, cosine theta. Theta is the rotation angle of the magnetic field, in-plane angle. And also here, this fitting is based on two terms. The first term is the same as here, sine 2 theta, cosine theta. But in addition to this term, there is another term, sine 2 theta. Then we subtract sin 2 theta. We got this equation. The torque can be described by this cosine theta term, and this is a constant because the sigma z is perpendicular to in plane. So magnetization of permalloy rotated in plane all the time. They are perpendicular. So this is a constant for sigma z signal. That's why we call this signal by this simulation. We could demonstrate sigma z signal is strong in this case. Just now we demonstrated the existence of auto-plane spin polarization sigma z in our system. In the following 2 or 3 slides, we demonstrate this sigma z can be modulated based on the modulation of the Néel order. The first technique, we use this ferroelastic string from PMPT 011 substrate. When we apply the electric field, we could see both tensile strain and compressive strain can be obtained in plane. That means we could get this tensile strain for in plane. In plane, we use this compressive strain to switch the magnetic switch to this direction. In general, magnetization of ferromagnetic system will be aligned along tensile strain, but for this antiferromagnetic moments can be aligned along compressive strain for this manganese gold. This is the spin torque FMR signals after applying the electric field. This positive 4 kilovolts per centimeter. After removing this electric field, we measure spin torque FMR signals. The current is along 100 direction. We could see just now the sigma z is very strong, and this symmetric signal has the same sign for this original state. But for this positive 4 kilovolts per centimeter, after applying this electric field, we could see the signal is different, indicating very tiny sigma z signal after this positive 4 kilovolts per centimeter. Because based on the XMLD signal, we demonstrate after the positive 4 kilovolts per centimeter, the Néel vector is switched 90 degrees to 101 minus 1 direction. So when we apply the current still along 100 direction, the current is perpendicular to the Néel vector. So there is no sigma z in this case. The sigma z is tiny. Of course, I have to mention that the switching cannot be 100%. So still some sigma z in this case. But when we apply the current along 01 minus 1 direction, previously for the original state, there is almost no sigma z in this case. But now we could see the sigma z signal is very large, much larger than before. Because of the Néel vector is switched to this direction, the current is parallel to the Néel vector in this case. So based on this experiment, we demonstrate that the Néel vector is switched by the ferroelastic strain from the substrate. Then the sigma z signal is also switched. Besides the ferroelastic strain, we also use the Néel spin-orbit torque to switch the antiferromagnetic layer. We use a current to switch the Néel vector of manganese gold from original 100 direction to 90 degree to this 01 minus 1 direction for 90 degree. We also measured the spin torque FMR signal. We could see the signal from sigma z decreases a lot after applying this new spin-orbit torque current. That means we also use the current to switch the Néel vector of manganese gold for 90 degree. In this case, the spin Hall effect from sigma j also also decays a lot. Also, I need to mention that the new Supermobile Torque of antiferromagnetic moments is also not completely. Previously, the Mainz group demonstrated the switching of the Néel vector of magnetized gold is almost 50% by this XMLD pin. So this sigma j signal is not decreased to 0. Now we want to do some control experiments. Here we use this platinum to replace magnetized gold in this case. Because platinum could only produce sigma y from our traditional viewpoint. This is the case, what we observe. We could see the symmetric signal in this case for the original state, or even after applying positive 4 kilovoltage per centimeter, this electric field, the signal is almost the same, indicating the fitting can be fitted by only from the signal from sigma y. So there is no sigma j signal in this control sample. Somebody will ask, there may be some exchange bias, exchange coupling between magnetized gold and permalloy contribution to the some signals here. So we use a copper layer insert between magnetized gold and permalloy to decouple the coupling. In this case, we could see the spin current could also flow through this copper layer because this is a very light metal. Copper is a very good conductor for spins. We could see when we apply the current along 100 direction in this sample, that means the current is along the Néel vector. Then we could see the very large signal from sigma j in this case by the fitting. But when the current is along 101 direction, perpendicular to the Néel vector, the sigma j signal is quite tiny. Almost the signal is from the sigma y to induce the torque. But after applying positive 4 kilovoltage per centimeter, the Néel vector changed to 1 direction. Then originally no sigma j signal, but a large sigma j signal in this case. In this sample, we could see very large signal from this asymmetric signal indicating very large anti-damping torque from sigma j in the two cases. Just now we demonstrate spin out of plane spin polarization and the antiferromagnetic spin Hall effect. That means we demonstrate that this spin Hall effect can be modulated by the electric field and the current. The Néel vector is switched 90 degrees, then the spin Hall effect is switched. We call it antiferromagnetic spin Hall effect. Then we try to use this out-of-plane spin polarization to do some spin orbital torque. We try to observe something unusual. The first experiment is this we grow permalloy on the top of magnetized gold. This is the in-plane permalloy. The z-axis of permalloy is a non-100 direction because of the substrate of PMPT. And first, we preset the magnetization of permalloy along -100 direction. -100 direction. Then we drive the current in this system, in this magnetized gold, because a combination of sigma j and sigma y, we could see this field-free switching of permalloy. This is somehow like this type X configuration because permalloy is in-plane magnetization. So we could get this field-free switching in this type X. But surprisingly, when we cannot switch back to this minus 100 direction, even we do these measurements, we cannot switch. In this case, we preset the magnetization to 100 direction, but we cannot switch back to minus 100 direction. This is also the same. We drive the different current, because when we reverse the current, both sigma y and sigma z are changed. That means both of the sign are changed. They are changed simultaneously. So in this case, we could think that sigma y is somehow mainly for the switching. Sigma z is mainly for behaves like this effective field for the type X configuration. This is the type X field-free switching. We also demonstrate type Z field-free switching in this sample. We grow perpendicular cobalt palladium perpendicular magnetic anisotropy layers on the top of manganese gold. We also measure this spin-orbit torque switching and zero field. Also, there is no exchange coupling for these two layers. Previously, we also demonstrated that the exchange bias, even though the new temperature of manganese gold is high, but the exchange bias is tiny and room temperature. Of course, the exchange bias is quite large and ultra low temperature, for example, and 10K. But for this room temperature measurements, we could see this field-free switching, which is not due to this exchange coupling. It's due to the sigma z switching. We also use different material, for example, cobalt nickel on the top of manganese gold. This is not easy to get this PMA cobalt nickel on the top of manganese gold. We spend a lot of time for this sample. We grow this PMA sample. We also demonstrated the samples and different magnetic field. We could see field-free switching and field-free switching here, and also there is no switching when the assistant field is minus 300 Ørsted. So we demonstrate field-free switching both in this cobalt palladium and cobalt nickel samples grown on the top of manganese gold. This is the type Z field-free switching. Then we try to explain somehow about this, how this sigma Z and sigma Y features in this SOT switching. What are the roles? Here is our macro spin simulation. This is very traditional macro spin simulation based on sigma y. We could see when the assistant field is applied along positive direction, the switching is from upward to downward. Of course, when the same current, but the assistant field is opposite, the switching is also opposite. This is very traditional simulation for this sigma y. This is for permalloy, for example. This is for platinum for sigma y. But for sigma z, even we apply the magnetic field positive and negative, the switching is the same. This is different from sigma y. And also, based on the simulation, we could see the field-free switching from upward to downward even without any field. This confirms our observation of field-free switching by in this manganese gold system, manganese gold PMA system. Then we try to understand the so in this case we could demonstrate sigma z itself with the magnetic field. It is not sensitive to the magnetic field, but here we demonstrate our switching is sensitive to the magnetic field. Then we try to understand with a combination of sigma y and sigma z. Of course, this is a very traditional viewpoint of sigma y SOT switching. When the assistant field is positive, the switching this is clockwise, this is anti-clockwise. But for sigma z switching, it's not dependent on the assistant field. So they are switched the same all the time. But then we summarize the two different signals together. Then in this negative field, we could see a combination of sigma y and sigma z produce the switching in this case. In a very large positive field, we could see sigma y dominates in this case. But in a very small assistant field, sigma z and sigma y, in this case, sigma z is dominated in this case, but on this boundary, sigma z and sigma y induce the torque somehow comparable. So they could not switch the magnetization in this case. So based on this simulation, we could understand the contribution from both sigma y and sigma z. Then furthermore, we try to understand field-like torque or damping-like torque, which turn contributes to the spin orbit torque. This is a field-like torque, damping-like torque. Both of them are 0, so there is no switching. Only field-like torque, there is almost no switching, but damping-like torque could produce the switching from downward to upward. We could see here that this is somehow like this spin transfer torque, the switching by this sigma z from downward to upward. In contrast, when we drive this negative damping-like torque, the switching from upward to downward. So we demonstrate damping-like torque should be the main component in sigma z field-free switching. We also want to mention that this sigma z switching combines the advantages of spin orbit torque and spin transfer torque. Spin transfer torque is very, this is upward, downward, is very straightforward for the switching for this PMA system. Also, spin transfer torque is based on this damping-like torque. Of course, our spin source is from collinear antiferromagnet magnetized gold. So this is also the spin orbit torque configuration. So our sigma z system demonstrates the advantage combining spin orbit torque and spin transfer torque. It would be a selection for the high efficient spin orbit torque for spin orbit torque M1, I think. Then I summarize my talk today. The first, we control of the spin orbit torque by magnetic mirror symmetry in this non-collinear antiferromagnet system. The second, we observe antiferromagnetic spin Hall effect in magnetized gold. These antiferromagnetic moments can be switched by both current and voltage. Following this, the spin Hall effect is modulated. That's why we call this is antiferromagnetic spin Hall effect. Based on the spin torque FMR signals, we demonstrated that both field-like torque and anti-damping torque contribute for the sigma z switching in magnetized gold permalloy bilayers. We realize field-free switching in both in-plane type X and out-of-plane type Z magnetization. Based on the simulation, we also try to understand the role of sigma Z and sigma Y in our system. Finally, I would like to thank my the contribution from several groups. The first is my group in Tsinghua University, Xianzhi and Xiaofeng, Baihua and Youfeng, and also Professor Feng Pan, and the group in Singapore, Professor Wen Su Yang's group, for some spin torque FMR signal measurements. Also, Xiaonong Fan's group in Nanzhou University for spin torque FMR measurements. We go the group for the measurements. Our investigation is supported by Natural Science Foundation of China and the Ministry of Science and Technology of China. Okay, thank you very much.
Thank you very much for the very interesting talk. We can use reactions button to clap. And if you have any question, if you're on Zoom, you can use the raise hand function. It's also now located in reactions button. And if you're watching this on Twitch, please just type your question in the chat box and I will read it for you. So do we have any question? Let's see. Kirill, you can ask the first one.
Thank you. Very interesting talk. So do I understand correctly that in order for this symmetry breaking to occur, the antiferromagnet has to be in a single domain state, or at least with a preference of one of the two types? Because the two domains are related by time reversal, yeah. Right?
Okay. This is a good question. I think one kind of domains is dominant in our system because of the especially the substrate of PMPT. So
no, but I don't mean domains related by 90 degrees. I mean the domains related by time reversal. This one and this one. It cannot be imposed by strain.
Yes, I understand your question. This is also the question when we substrate the paper during the review process. We think there is one kind of domain is the dominant in our system. This is indeed difficult for the characterization at this moment. But if we want to get this signal, there should be one main domain in this case.
But is it just because the domain size is not small compared to the size of the sample and it just randomly prefers one or the other? Then does that mean if you produce a bunch of samples, then some of them will have a positive effect and some of them will have a negative effect? Is that what you observe?
From our measurements, we do not have these opposite signals so far. Of course, this we need to understand further. Thank you for your question. This is indeed very important.
Thank you.
Matthias, please go ahead.
Yeah, thanks for this interesting talk. I have a question about the manganese to gold permalloy. I mean, we observed a very strong exchange bias, very strong coupling between the manganese to gold and the permalloy. Did you, I mean, in the copper palladium, the exchange bias at room temperature was relatively small, you said.
Okay.
How about in the manganese permalloy, manganese to gold permalloy?
Yes, we also measure manganese. I also check your paper, the paper from your group in MENS analyst. Yes, this advanced materials paper in 2012 in my memory. This is your first publication on manganese gold. We could see there is almost no exchange bias between manganese gold and iron.
Yeah, but now in permalloy we see extremely strong coupling, like 5 kiloarsted.
Yes.
So,
but
so did you ever look at that?
The exchange bias, there is no exchange bias and the room temperature, but the exchange bias is large when we cooling down to 10K.
Okay, thanks.
you. Do you have other question? Danwook, please go ahead with your question.
Thank you very much for your interesting talk. I have a question somewhat similar to the previous question by Kirill. So you demonstrated the switching with manganese to gold and permalloy. So in manganese to gold, there are two magnetic layers. So my question is whether the termination of the manganese to gold affects the sign of the sigma Z that you have demonstrated.
Oh, okay. In my memory, you are a theoretical researcher.
Yes, I am. Yeah.
Yes. Previously, I read your paper on this orbital.
Yeah, true. Yeah, thank you.
Yes. Okay. Well, so far we do not investigate in so details. So we just grow manganese gold and then deposit the permalloy on top. We grow different several times. All of them shows almost the same behavior. So we so far we don't know what whether the termination will work on this system or not. So maybe theoretical work should help here.
I think as Kirill mentioned before, two different terminations of manganese to gold, they correspond to partner for time reversal symmetry. So yes. I think in principle, they should change the sign of sigma Z as well.
Especially so far the growth is not so perfect. We cannot control. So and first the interface is not atomic smooth.
Yeah, sure. Yeah.
We cannot do this at this moment. Of course, in future, if we could improve the growth by MBE, for example, we try to do this in future. This should be interesting if we could control the termination manganese A or manganese B. This may show different signals.
I see. So do you think there is more dominant termination in your sample then? Just according to your experience on your samples.
Let me see. Maybe this happens, but I don't know at this moment.
Okay, yeah. Thank you very much for the interesting talk.
I would like to mention this is a bulk effect. The spin from the bulk. So the termination may works, but maybe not so critical.
Okay. Sorry, I didn't know this effect very well, so maybe my question was already wrong. Okay.
The spin Hall effect from the bulk. Yeah.
All right. Yeah. Thank you very much.
Thanks.
Kirill, do you have a follow-up question?
Yes, I actually probably more of a comment about these things, the termination, bulk, and surface, etc. So one thing to bear in mind is that in this material, which does not have macroscopic time reversal symmetry, if you have a single antiferromagnetic domain in the bulk, it comes with a surface magnetization that is coupled to the antiferromagnetic order parameter. And it exists even in the presence of surface roughness, because the two terminations with spins to the right and spin to the left, they are just structurally distinct and they have different energy. So no matter what roughness you have there, in thermodynamic equilibrium or not, no matter how you grow it, you will always have magnetization at the surface. So you can have an effect just from that, from interfacial effects. So a priori, you can't know whether it comes from bulk or surface unless you study something like thickness dependence or maybe sensitivity to the surface. You just don't know. So this is one thing. And the other thing is maybe more of a suggestion that because you have this surface magnetization, then in principle, because you have it coupled to a ferromagnet, then if you anneal your sample from above the Néel point of Mn to gold, if it's possible, while having the ferromagnet aligned in the external field, you will create a preference, just like in the exchange bias, but in this more of an equilibrium sort of way. You will have create a preference for one type of antiferromagnetic domain. And if you can freeze it, then depending on the initial orientation of the ferromagnet, you can change the sign of your ultimate effect in the end.
Oh, these two suggestions are good. The first is, I think we need to think about this interfacial problem to see whether the interface plays some role in this system, because this is just the first try in our group. We do not work so much details. For the second is also for this annealing, the new temperature of manganese gold is indeed very high. Is from theoretical calculation is higher than 1000 K. So, and first the experiments are not easy to realize. But if we increase the temperature as high as possible, it also could fix some of the near water. It should also affect the measurements. I think this is a good question we need to do later.
Yes, I agree. Thank you.
Yeah. Okay. Thanks.
We have a few people raising hand. I'm just going to ask them in the order I see them. The first one will be by Dr. Ren Chen. Please go ahead.
Hi. Hello. Hi.
Hi.
Thank you for the very interesting talk. So I have a conceptual question. So when there's an autoplane spin accumulation generated from the manganese gold, and this spin accumulation is absorbed by another material, then the system is losing angular momentum along the z direction. So by the conservation of angular momentum, then there should also be a back action acting on the manganese gold, the antiferromagnet itself. So I understand that you mentioned that spin angular momentum is not conserved in this process, but by continuously providing spin angular momentum to the outside, the system will, unavoidably experience a back action or a spin torque acting on itself. So I was wondering if, is this effect ever exists, or yeah, that's my question.
Thanks. This may happen. Our physical picture is based on this Sinova and the PRL paper, and later the Spintronics Torque in this gallium manganese arsenide. Maybe you know the work in Nature Nanotech in 2014. They demonstrated the very curvature spin orbital torque in gallium manganese arsenide is somehow like half of our physical picture. Then we just make them together because we think the model works in our system, especially for this local reversal symmetry manganese gold system. We combine this. That means this is the opposite, two different opposite gallium manganese arsenide combined together. Then we use this physical picture to describe our generation of sigma z. Maybe some other understanding from as you suggested. I think we could discuss this in future. Maybe some other understanding for the generation of sigma z in the system.
Okay, thanks.
Professor Christian Beck, please go ahead with the question.
Yeah, thanks. So thanks, Cheng, for this very nice talk. I have a question concerning these STFMR measurements on permalloy manganese to gold, where you showed that you have strong or weak field-like torque depending on the current direction. So in the strong case, is it strong enough that you can actually see this as a resonance line shift?
And you mean the magnetic field dependence, or?
Well, depending how you do the measurements, but you should see a shift of the resonance field, right? If you have a strong contribution to the field-like torque. And I can't really see it from the plotted data.
I think this also I need to check, and we measure this is under this 5 gigahertz spin torque permalloy measurements. We also measure different and different frequencies. All of the data have the same tendency, but sorry, I do not go deep into this fitting.
Okay, thanks. It should be in the data. I mean, you should just have a look at it, I guess.
Okay.
May I also want to comment on it? I think this is the rectification measurement. So all the torques are in microwave frequency. So I don't expect you to see any shift of the resonance along the field direction. Are you referring to applying a DC current to cause a shift?
Yeah.
Okay, that's the point. Yes. Okay.
Also, that's why we also do these angle-dependent measurements, because something may happen for these field-dependent measurements. Then we also use these angle-dependent measurements to confirm the signals.
Okay. That's Dr. Fei Xue, please go ahead with your question.
Okay, so just regarding to Doug and Curious questions, so I think it depends on the termination of your magnetic or manganese atoms. This is very similar to tungsten ditelluride case, which each model layer has different in-plane mirror symmetry breaking or polar order. So if you imagine that the spin-orbit torque exerted on the ferromagnet is coming from this ordinary spin Hall effect in the bulk. So you have, it depends on which termination means determine your in-plane polar symmetry order. Of course, the interface breaks this out of plane polar order, but not in plane. So that's my comments. And then also regarding to Doug's questions, it does not care about the copper layer, because this interface is this termination only care about which manganese atoms on the surface, whether it's come from the copper interface or permalloy interface, doesn't matter. If it's purely from a bulky effect, if something like that, of course, interface can play other roles.
Okay, for I answered the second question first, because this indeed for when we insert a copper layer between the manganese gold and permalloy, then we see the torque is somehow different, especially after the inserting copper. The anti-damping torque becomes much larger from sigma z.
But the sign cannot change, right? I mean, it's the same sign.
You mean here?
Yes. But anyway, if you insert the copper layer, you're not sure about the termination anyway, if you're not looking at with some atom smooth spectroscopy, I guess. Yeah, so you never know that. In the Cornell group, they actually are, they are accidentally they have this tungsten ditelluride, they accidentally have one step between in the two domains, right? One step is certain tungsten ditelluride, the other step is the opposite. So they observe this opposite sign. But here I don't think if you didn't have that accident, you probably could not determine that anyway.
This is a good point, especially to answer the question of from Kirill. Because we insert this copper, the sigma Z signal still here. But we also see the field-like torque and the anti-damping torque become somehow change after inserting copper because of interface transparency may be changed by copper. And also, I think there's some, because of the existence of copper, the direct coupling between manganese gold and permalloy is different. Then more damping, anti-damping torque behaves here. So after inserting copper layer, the main feature is the same, but some details goes to different, especially on these two torques.
Yeah, that's right. Yeah, thank you.
Great. Do you have another question? It looks like we have some discussion going on in the chat as well. I would defer that to the discussion afterwards. If there's no other question, let's thank the speaker again.